Hey, this is Warren Redlick. I had a great interview last week with James Douma, who is an expert on artificial intelligence and seems to know a lot about Tesla full self-driving. This is the first in a series of videos from that larger interview, breaking it down into smaller chunks and edited for brevity and also edited to improve the sound quality. In this video, we talk a lot about inputs to FSD and outputs from FSD. Are you ready? Let's go! What differences, if any, do you notice between the FSD in your car and the FSD Beta that you've ridden in?
FSD in the cars today, there's no FSD in the FSD that you get if you don't have FSD Beta. What you have is a set of features that are essentially add-ons to Autopilot that make it a more capable level 2 system, but they do not at all make it a level 3 or a level 4 system. I mean, aspirationally, maybe they eventually get there, but they don't have they're not feature complete for doing that. That is, FSD includes features like nav on autopilot, right? So nav on autopilot, if you have that feature and you use it, it's capable of, if you get on a limited access highway, it can take you from like an on-ramp to an off-ramp, including all the interchanges. At least aspirationally, it can do that. It's not perfect at doing that today, but it'll do lane changes and it will deal with traffic on freeways pretty intelligently. Now, I mean, the bar keeps coming up, but its ability to interact with other drivers, to make lane changes, to avoid people who are doing stupid things or acting, basically if somebody changes lanes into you from a blind spot, and you don't notice them, autopilot will get out of the way, right? It will take that intervention itself. So nav on autopilot has a whole stack of these sort of incremental features that add convenience features to the core level 2 capabilities of autopilot, but which do not attempt to solve the whole problem. To solve the whole problem of being able to go from any point in the world to any other point in the world, there are lots of corner cases and lots of special rules that you need to tack on to the way that Tesla is doing autopilot now. So just broadly speaking, Tesla uses neural networks and they use quite sophisticated artificial intelligence techniques to deal with perception in the world. But for the most part right now, they are taking those perceptions and then they are hand coding a set of heuristics, which are basically rules for, like, in this situation, do this. And that whole stack ends up sort of creating the set of things that autopilot can do, or FSD Beta can do at this point in time. FSD Beta, the version of the code that I've seen, the version of the neural networks that I've seen, is clearly designed to work inside this environment where there are humans writing a bunch of rules, but the network itself, the neural networks themselves are producing these relatively highly abstracted perceptions of the world. For instance, the neural network doesn't have to be restricted to, there is a car of this kind at this position relative to you, right? It can say stuff like, there are no cars about to merge in front of you, or there is a car about to merge in front of you. We do not want to be at this location, this position in the lane right now. It's once upon a time, autopilot was basically on rails. It drove right down the center of the lane. And now autopilot it takes a more holistic view of the situation that the vehicle is in and decides where in the lane it ought to be. That's how it can move over to avoid a cyclist or a motorcycle when it comes on. So when they do that, they don't have to heuristically, with a set of human written rules, sort of say, oh, here's a motorcycle and it's at this location, and let me look in my table to see how much space I should give a motorcycle. Okay, move the car to the left 4 inches. Instead, what they can do is they can just ask a neural network, given the whole set of vehicles around you and the stuff that's coming up, where should I be in the lane? And the neural network will have a proposal, and then they can decide to go to that proposal given heuristic constraints that they might choose to apply. So as the neural networks get better, the way they describe the environment, the information that they pass to the people who are writing the rules for how to drive the car, are more sort of human-like. They're higher level abstractions. Instead of having to be simple, concrete descriptions of specific physical things in the world, you can ask more general questions about the environment. Like, in this situation, what would you recommend should be the easiest path forward? And the neural network can look at the available space. It can look at where the other cars are. It can look at whether there's construction cones and all that kind of stuff. And it can say, this is the proposed, path of least resistance through this environment.
One of the thoughts that I had to try to break down what FSD really does is to start with this. What are the major inputs to FSD? And my impression, I think the major input is cameras, that there's 8 cameras and each camera is transmitting pixels. You know, maybe it's 1024 by 768, maybe it's 1280 by 7, whatever. There's some 1920 by 10.
1280 by 960 3-color HDR cameras.
And there's 8 of them.
There are 8 cameras. 7 of them are different than the 8th one. The backup camera actually has a different color space. The backup camera, I suspect the reason that the backup camera has a natural color space, a conventional RGB color space, and I suspect that the original idea with that was that people are going to look at it for backing up, and you want the bushes to be green and the concrete to be gray, and you want everything to look the right color. So they picked a conventional color space. But the other cameras on the car, they were originally intended to only be used for driving related functions. And so they picked a color space and a dynamic range for those cameras and a resolution for those cameras, which is optimized for the task of driving. It has good resolution and dynamic range for the information which is most useful for driving. And it doesn't concern itself very much with whether, if a human being were to look at an image from this camera, does it look natural?
I want to try to understand how FSD works. And what I understand is there's this chip in the car, or there's 2 chips in the car that are known as Inference chips, which I'm going to ask you about Inference later in this conversation. But there's a lot of pixels coming in. There's what I would see as a black box, and then something comes out the other side. There has been in the past, or there currently is maybe in your car, radar is another input. Maybe sonar is an input. Are there other inputs besides the cameras, radar, and sonar that go into the FSD inference chip that it processes to get to its outputs, which we'll talk about shortly?
So that changes over time. Where you draw the boundary of the black box changes the answer to that question, and when in time you ask that question, because it's something that is worth keeping in mind about both Autopilot and FSD is that there isn't really a definition of what it is, because the definition evolves. Having watched the evolution of the system over time, I can tell you they are constantly doing a large number of experiments. There's a ton of stuff in there at any given point in time, which is not driving the car. It is experiments that the AP team are pushing out to the field to try something to resolve. They're constantly trying to add new functions. And when they add these new functions, they try things. They don't sit down. They're not doing the Boeing approach where, you try to prove the thing works in simulation and then you just write it and push it. They push test versions out to the fleet. They see what they do for different approaches to dealing with certain things. And then they refine the approaches that do work, and then they down select and add the feature at some point in the future. So what Autopilot is at any particular point in time is this moving target. Like literally every time they push an update out, it's different. They've added some features, they've added some experimental stuff, they've pruned off some things that weren't working as well, they've refined some other techniques. And at any particular point in time, they may be pushing many different versions to many different vehicles. So they're running a lot of experiments in parallel all the time. I think it's probably better to think of this as a giant work in progress and not a finished product. I mean, we're all driving, some intermediate revision of something, which eventually is going to be better, and which probably doesn't have a stopping point. Right? I don't think even after the cars are out driving themselves around and you can do robotaxis, there'll be things it can't do. It won't be good at snow. It won't be good. Maybe it can't handle a situation where a camera is out. Maybe it's not as good at facing straight into the sun. Maybe there are dynamic traffic situations it's not as good at. And they're just going to keep adding these features. And I think it's going to continue to be a work in progress for decades, right? And as more people drive it and Tesla pours more resources into it, it's, the effort's going to expand. We're on hardware 3 now. There will be a hardware 4, then there'll be a hardware 5, because the silicon is going to keep getting better. The software is going to keep getting better. The one thing I would say they probably won't change is I think they probably won't change. They're reducing the number of sensors. I think they'll probably go down on the number of sensors. They might go to higher resolution cameras. And I had thought at one point that maybe they would go to multispectral cameras or thermal cameras. There's a lot of other sensors besides like sonar, radar, and LiDAR and cameras that you could potentially throw in there. And there are a lot of them are inexpensive. They haven't been looked at very closely, but it does seem at this point like they're going to double down on cameras and they're just going to keep pushing that. And I mean, to be honest, that what you could achieve with the sensors that they have now, I mean, they're very, very far away from hitting the limits of what they can do with the 7 cameras they have in the car. They could keep just pouring resources into compute and resources into software and training for 10 years, maybe, before the sensors are going to start being the limitation on what they can do.
My impression is Elon said we're ditching radar. So it seems to me the primary input to the FSD chipset is the 8 cameras and not much else. Maybe the sonar is a significant input, but my impression is they're trying to do this on pretty much vision only for a while. Does that sound right?
So right now there's kind of there's a perception stack.
Yes.
So let me take a step back from that. So driving is perception, planning, and then action on top of that. Perception right now is totally dominated by the cameras. Planning is kind of a 50-50 split right now. They've got neural networks that are doing some of that, but a huge fraction of that is getting written heuristically. And action is completely heuristic. That's all handwritten code.
I think you speak at a higher level, and I think I understand what you're saying. So,
okay.
Let me try to take this away. I think this is going. The first step for the FSD chip and software is to see the world, perception, identify objects. I'm not sure where this fits in there, but it's like identify where it thinks objects might move, right? Is that still in perception?
Understand the situation,
right? But
that's perception.
So I've seen Elon talk about probability vectors. I saw Jim Keller with his interview with Lex Friedman talk about, ballistic probabilities. My sense of it is the first step for the FSD chipset and software is identify objects that are on the cameras. And possibly things that aren't on the cameras, but things that you were there before and they're occluded, but they're supposed to be there. But identify objects and then assign ballistic probability vectors to them. I think, for example, stop sign shouldn't move. The ballistic probability around stop sign is it doesn't move.
Ideally, yeah.
Car coming from the right, it's currently moving at this velocity. Ballistic probability, it's probably going to keep moving in the direction it's moving. And there may be some variability to where it thinks that object might move, but is that still in the perception part of the stack that you're identifying objects and you're predicting where they're going to move?
Yeah, that's perception.
Is there something else in the perception stack?
I guess depending on how you talk about it, you could imagine different things. But I mean, just super broadly, perception is tasked with understanding what's the current situation, and that includes not just the current positions, but the future probabilistic trajectories of everything in your environment, including yourself.
Right.
Okay, planning is, this is my situation, this is my goal, what do I want to do to achieve my goal given this situation? So perception looks at the world, tries to provide the current situation. Planning tries to take that situation and the objective that you have, that you've been given by your user, and determine what the best course of actions is. And then the third stage is doing those actions.
I'll just give you my rundown of what I think it's doing, and you can tell me if I've got it wrong or if I'm missing some details. So the first part was observing objects, predicting probability vectors. For me, the planning part is, okay, we're trying to get to this point. Let's minimize the probability we hit something, right? We still want to get there. We want to try to maintain our speed. There's some modification, because you could minimize the probability of hitting anything by not moving. So you have to have some part of the objective function of getting to where you're going, right? But a large part of
your goal is to get somewhere, then not moving is not an option.
Right. To me, there's an objective function. It's like, get to this place and don't hit anything. And there has to be some non-zero probability of hitting something in order to be able to get where you're going. I mean, you're trying to minimize the probability. You're trying to get where you're going. I mean, does that sound like the rough idea? I think we're going to leave out, I roughly agree with you that the execution of the plan is probably still heuristics. So I think I've seen them talk about, maybe it was you, maybe it was Andre Karpathy, that ultimately the machine learning is going to eat even the the execution of the actions.
Yeah.
But for now, I think my impression is that planning the path is now pretty much fully, the machine learning is planning the path. Do you think that there's still some heuristics?
No, it's if you've watched the FSD videos, you'll notice that there's this little line that comes out of the front of the car, and sometimes it angles around other cars, or sometimes it turns corners and whatnot. That line is output by a neural network. It's coming out of a neural network because in order to do that line, in order to be able to make that line, you have to take into account a whole lot of things that it's very difficult to like write all the rules for. Is there a bus? Is there a biker? What angle is this street? Is there a stop line? What stage is the light? Is someone running the light? Just on and on and on. Like what's the appropriate path? If you come up behind a vehicle that's stopped in your lane, is that a bus pulling over to drop people off? Should I wait? Is it safe for me to change lanes to go around it? Or, do I go around it? If I go around it, do I start my lane change 100 feet back? Do I go up behind the bus, stop, wait, and then there are a lot of things that go into figuring out what the shape of that line ought to be. And they've been producing that line with the neural network now for 18 months or 2 years. I mean, they started much earlier than I expected them to. Like, I was surprised when the neural network started outputting that path vector. So now that path vector, it's an input to planning. That vector is a component of planning that makes the job of the person writing the code that does the planning a lot simpler. So right now, you don't feed a Google map into the planning network, and then it figures out what your route is, right? The planning thing, it takes a Google map and it executes an A-star algorithm or something like that to sort of figure out, like, to get to my destination, what are the turns I want to take? What roads do I want to drive on? And then the planning network that's actually driving the car, it's just taking a tiny little bit of that at any given point in time, right? It's looking at, like, for the next, what's the next segment of my drive? Like, how far am I going before I do a turn?
So
right?
the FSD might be looking 100 yards ahead. It's not looking 5 miles ahead.
Yes.
Okay.
I mean, well, in a sense, it's easy to get confused about what part is the AI. FSD is the whole program, right? Yeah. Which includes the call to the Google Maps.
Sorry, the neural network.
And actually, I kind of, right now, I like to use the term autopilot as opposed to FSD.
Okay, but the neural network is maybe looking 100 yards ahead, but there's other code that's yes. doing the long-term planning of this is the route we're going to take to get to our destination.
At this point in time, to a first approximation, you could say the neural network is only concerning itself with the volume of space which can be directly perceived, right? So if you can see 100 feet down the road, if you can see 200 feet down the road, the neural network is taking that into account. It is not taking into account anything that it can't see.
Well, it may have seen an object
from temporary occlusions.
It may have seen an object go behind something and figure that thing might come out the other side and be aware of it. Okay, right. So the input is largely pixels coming from the cameras, and the output is largely a path. Is there other bits of the output from FSD from the machine learning part of FSD or Autopilot?
Okay, the output is not a path. The output is thousands of discrete. I think there are approximately 1,000 tensors that come out of this. So each individual tensor is a block of data that represents some aspect of the world that the neural network has been tasked with providing an evaluation of. One of the neural networks produces a tensor for the front main camera, which is what is my drivable space, right? So there's a drivable space tensor, and what the drivable space tensor does is, it's a field that basically maps onto the field of it. It's a two-dimensional set of numbers that describes the likelihood that you can drive on any particular piece of ground in front of the car.
Okay.
Right. So, for instance, a K barrier would not be part of it. The asphalt you're driving on would definitely be part of it, and then the shoulder might or might not, and then the field adjacent to the road, or driveways that are adjacent. All of these have different representations in the drivable space map. So the drivable space map is just one output from the network. Now, that drivable space map isn't necessarily being used to generate the path vector, but it is useful to the guys writing the heuristics that control the vehicle, because there are a lot of rules that they might want to write to add to that path vector. Like, for instance, if I think this car is about to pull in front of me, slow down to give him time to, if you're coming to an intersection and a driver pulls up and they're going to turn right and they're going to turn right into your lane, any human being approaching that intersection, you watch that driver because he might not see you and he might turn in front of you, and that creates a challenge for you. So there are people writing heuristics at this point in time to basically evaluate that situation. So the neural network can help by providing a probable path for that. The neural network can also do a thing like, did the driver look at me? Can I see his face? Right? That the attention thing that you do, and that's a thing a neural network can actually do pretty well.
But let me
to try to infer the intent of a vehicle based on its motion and position and the other vehicles around and that sort of thing.
My image is you have the FSD chipset, and a bunch of pixels are coming into the FSD chipset, and something's coming out of the FSD chipset and going to the machine that whatever software or hardware drives the car, right? So when you say there's 1,000 tensors,
FSD drives the car. The output of the FSD is the frequency and amplitude of the current that or the voltage that you're going to apply to the steering motor. Like at the end of the day, that's
but I mean, there's these two chips that are known as the inference chips. I'm trying to narrow right in on the inference chips. That there's, if I'm correct, there's pixels coming into the FSD inference chips, and there's some sort of data coming out of the inference chips. There's these two chips, right? They're sort of supposed to be redundant chips, right? That were displayed at autonomy
day. There's two SOCs in what Tesla calls the FSD self-driving computer. So when you describe a single board, it has two SOC. A SOC is a system on chip. So it's a 14 nanometer TSMC, or it's a Samsung silicon, but the SOC contains the overwhelming majority of the simple computational. When I say simple, not to suggest it's simple, but for instance, there's a power supply and it has silicon, which is separate. And there is silicon in the FSD computer, which is not in one of the SOC chips. But there are these two redundant SOC chips and each SOC has 12 ARM cores. It has a sizable GPU. It has two of the neural network, matrix multiplier units, and it's got a ton of other stuff. It has a vision pre-processing engine. It has encryption hardware. It has, there's a bunch of little specific processing units that go in there. But by and large, the overwhelming majority of the computation in the system is happening on one of these two redundant SOC chips. But they're redundant kind of in the ways that the two engines on an airliner are redundant, right? Yeah. That is to say, if you lose one, you can still operate, but they're not mirror identical copies doing exactly the same thing.
I'm just trying to get a grip on. To me, the cameras are not part of the system on a chip. And the accelerator and the brake pedal and the steering wheel are not part of the system on a chip. So in the car, the data's coming in from the cameras, and something's coming out of the system on a chip to go to the steering wheel, the brake pedal, and the accelerator pedal. And to me, or I don't know if they go directly to that or if it's drive-by-wire or whatever, however that's working.
It's a command over a CAN bus that interfaces to a controller on the motor for the steering system. Yeah.
So I'm just trying to get a feel for this is my monkey brain trying to get a hold of this neural network process, because you mentioned the matrix multipliers, right? And, we're going to head to Dojo or the training part in a minute, but it's taking in data from the cameras, and it's somewhere along the way, instructions are coming out. Here's where we're going to go. So somewhere in this process, you've got video in, it perceives the world. There's some kind of path planning, and instructions go out. Okay, here's where we're going to go. Am I in the ballpark of correct with what this is doing?
Yeah, no, that's right. The camera feeds come straight in. Right now it talks to the radar over the CAN bus, and there's a sonar controller somewhere in the system, and it talks to sonar controller over the CAN bus. So a CAN bus is kind of like a little Ethernet network inside the car. It's got CAN buses that it uses for talking to other, smart systems elsewhere in the vehicle. But yeah, I mean, it's overwhelmingly pixels coming in and the system deciding based on pixels what it's going to do. But the process for decision is, you pre-process the video, you have to get it into a format where a neural network can digest it easily. Then you feed these cameras into a whole array of neural networks. Right now there's a bunch of different neural networks. At any given point in time, there's some neural networks that are driving the car, there's some that are experimental, there's some that are just used for like looking at the world and gathering data for Tesla to do future training on, and that sort of thing. So all of these networks process these images from the cameras, and sometimes you have multiple independent networks associated with a particular camera. Each of these networks outputs a large number of pieces of information about what it sees that they've been trained to do. And so you've got these thousands of blocks of information that come out, and those are going into code that a human being wrote, right, to make decisions about driving, right? And then the output of that is going to be a set of instructions that go to these controllers that turn the wheel and press the brakes and so on.
I just thought you'd appreciate that. Rexy the Hound said, "This is like watching a Boeing engineer explain how a 747 works to a caveman." I'm pretty sure I'm the caveman in this story. In part 2 coming up, we're going to talk about understanding Tesla's FSD from a subjective perspective, how it feels to me or how it feels to you, and from an objective perspective, what can we see in the hardware and the software and the performance that can be measured objectively that tells us how it's doing, how it needs to be improved, and how it's doing overall. Please support this channel on Patreon. Check out the t-shirts. Machine That Builds the Machine is one of the most popular shirts. Links to both of those in the description below. Check out other videos on my channel, including the one that's coming next. Thank you so much for watching.